So, our next talk will be about hardware, firmware, reverse engineering, side channel analysis, fault injection, and that all to gain code execution on a custom chip. A lot of things, a lot of buzzwords. And I wish you a lot of fun with Thomas Roth aka Stacksmashing, with the talk Ace Up the Sleeve, hacking into Apple's new USB-C controller. Have fun, and a big round of applause.
Thank you. All right, let's go. Hey everyone, welcome back to Hamburg. My name is Thomas Roth. I'm a security researcher for hardware and firmware. I'm also a co-founder at Hackstry.io, and you can find me on most of the socials as either Stacksmashing or Ghidra Ninja. Now, as any research, this is based on a lot of other people's work. There are a ton of people who did prior art and previous work without whom I wouldn't be here. So first off, Sigusa, who wrote IO kernel RW and was around for a lot of questions and answers. Ollie for Thunderbolt Patcher, the Asahi Linux team for documenting a ton of the hardware that we will talk about. Carlo Maragno for being, my rubber ducky when it comes to fault injection. Jiska, Fabian, and Caro for just enduring my rants on broken technology. Marc Zingier for the central scrutinizer, and then the T8012 dev team who did initial research on the old ACE controllers. Now, this talk is almost like the third part of a trilogy, which wasn't the plan, but here we are. And so there's a bit of a backstory here. So if you know the old iPhones, they used to have the Lightning connector. And the Lightning connector does some obvious stuff, right? It has charging, USB, you can do video and audio over it, and so on and so forth. But beyond the boring stuff, it also can do some cool stuff. Namely, you can do JTAG, so debugging, UART, and also a protocol called SDQ via Lightning. And so 2 years ago, we developed an open source cable that allows you to access these buses, and we called it Tamarin cable. The idea was that we want to have a cheap and open source Lightning tooling that you can essentially build for $10 or so, and you can explore all these buses that previously you could only play with like $700, $800 of hardware. Unfortunately, Apple decided to throw all of our work away, and they essentially did this.
So we're bringing USB-C to iPhone 15. It enables charging, transferring data, playing audio and video.
Now, unfortunately, they forgot about all the cool stuff. Did they really get rid of, right? And so exactly a year ago, actually on the minute a year ago, in Azal 1, not far away, we talked about the iPhone 15 and USB-C and how we essentially built Tamarin C to access the USB-C bus on the iPhone and do some fun stuff, such as essentially setting some of the pins on the USB-C port of the iPhone to different buses. And so essentially this let us use some of the sideband use pins of the USB-C connector to do stuff such as UART, SWD, aka debugging, and also some other internal buses, for example, SPMI. And so exactly a year ago, we released this PCB called Tamarin C, which is essentially a small tool to play with USB-C on the iPhone. Is it my cable that's broken, or is it a switching issue? Okay, and so that lets us play with USB-C on the iPhone 15. And now on old iPhones, on the Lightning iPhones, all this stuff of like getting access to JTAG and so on and so forth is handled by a chip called TriStar or Hydra. It's essentially directly connected to some of the Lightning contacts, and it lets us configure the pinout essentially. On the newer iPhones, so the USB-C iPhones, this is done by a chip called the ACE3. And so you can already see physically the chip is much larger, and the picture is actually of the ACE3 of a MacBook, but it's almost the same. And essentially, this was pretty new with the iPhone 15. However, if you already can guess by the number ACE3, there's also previous ACE controllers. And so on previous MacBooks, hello? On previous MacBooks, there was a chip called the ACE2. And the ACE2 is essentially a tiny Thunderbolt / USB-C controller. Should we switch adapters? Let's go. Small technical difficulties. I guess it's day one. Pro tip. Setting a great example of randomly plugging USB-C devices into my MacBook. All right. Anyway, so there was a previous version of the ACE3 called the ACE2, which was found in a lot of MacBooks and so on. But you know, this is a USB-C controller. Why do we care? Well, on the iPhone 15, it's fairly interesting because we have the big SoC, the main processor here on top, and then the ACE3 on the bottom. And essentially, the ACE3 sits between the SoC and the actual USB-C port. And so on one hand, the ACE3 handles all the power delivery communication and sets up charging and so on. But it also handles something called VDM, or vendor-defined messages, so special power delivery commands that are used by Apple to reconfigure the USB-C port to, for example, get access to SWD, to UART, to actual USB, and so on and so forth. And all of this is done on the ACE3. And to figure out what commands and what can we actually do with this, given that it's apparently connected to a lot of internal buses, we want to kind of get access to the firmware of this chip to see what else is there. Are there maybe more secret commands, and so on and so forth. And so from the outside, this essentially looks like a power delivery controlled multiplexer. However, on the iPhone 15, when you plug it in DFU mode, so you press the buttons for 7 seconds, 15 seconds, whatever, it goes into the firmware upgrade modus. And when you plug the iPhone 15 in, it comes up as a mode called port DFU. And it turns out that port DFU is actually a full USB stack running on your charging controller. And so essentially, if you plug it in, it first goes into port DFU, and once you leave that mode, you actually only go after that into the actual DFU mode of the SoC. And so imagine if you remember Checkmate, which was a boot ROM exploit, imagine if you could run an exploit like this directly on the USB PD controller. Especially if you, essentially if you backdoor the controller, you will be gathering persistence on the device without actually gaining persistence on the SoC. And so this made me kind of curious, what can this do? I want to get the firmware. Now, as said, the ACE3 is not the first ACE, and we have the predecessor, the ACE2. And for the ACE2, we can actually get a datasheet, because the ACE2 is actually just a relabeled TPS 65986 from Texas Instruments with a custom ROM. And so, the first search was, maybe this new controller is also just a relabeled Texas Instruments chip. Unfortunately, it isn't. And so it's essentially a complete black box. We have a chip, it does something interesting, and we have no idea how it works, what it does. We have no pinout. At that time, there were also no schematics because the iPhone 15 and the MacBooks were super new, and so on and so forth. However, given that it's ACE2 and then ACE3, it was probably an evolutionary development. And so it's very likely that there will be a lot of similarities between these two chips. And so I decided to essentially look at the ACE2, because that one is already researched by other people, try to figure out what we can do, and then go from there and try to attack the ACE3. Now, the ACE2 can be found on all modern M1, M2, M3 non-Pro MacBooks, and essentially there's one for each port. And a couple of years ago, back on the T2 MacBooks, the T8012 dev team figured out that actually this chip has the debugging port enabled and that we can dump the firmware of it. And with that dumped firmware, they figured out all these old Apple Type-C port controller secrets, which were the initial ways on how we got serial on the MacBooks and so on and so forth. Unfortunately, for legal reasons, they couldn't just publish the firmware, and so I had to open up a MacBook of mine, shittily solder in some wires, and dump the firmware. Yeah. And after a bit of reversing, I found the main command handler of all the commands that this chip supports. And so essentially, there are different levels of commands even. There are special privileged commands, such as memr, memw, and so on. And these privileged commands essentially are like peek and poke. Unfortunately, they are disabled on production devices, but you will see why having these commands is super useful at the end of the talk. And so, yeah, we now know all the commands that it supports, and essentially we can send these commands from the SoC, from macOS user space, to the ACE2 via something called the Apple HPM bus. HPM stands for Host Port Microcontroller. And it's essentially just an API that talks to an actual I2C interface on the wire. And so there are some user space tools. So for example, you can run HPM diagnose if you have a Mac, and you will see that it like lists all the stuff that the chip does, and so on and so forth. Now these short commands that we can send over to this chip are so-called 4CC commands. It's essentially 4 ASCII digits that can just be encoded to a number. So it's a super simple protocol, and there are a couple of, you put the command in register 9, and then the status comes back in register 3, and so on and so forth. And I developed a tool called ACE tool based on Thunderbolt patcher to communicate to these ACE chips. And essentially this allows us to send commands. So for example here, the GAID command. And then in this case, the chip reboots. Now what's cool is, because we can read out the status registers, we can always see which status does the chip currently have. So for example, in this case, we are rebooting the chip. And even as it reboots, we can query the status on whether it's in bootloader mode or in application mode already, and so on and so forth. Again, this will become important later on. Now, next to the ACE2, there's also a SPI flash. And this external flash has some of the most annoying firmware to reverse I've ever seen, because essentially, it does not contain the full firmware, but instead it contains patches for the read-only memory that's burned into the chip. And this makes reversing hell. Essentially, each function call in the firmware goes to a segue function, which then dereferences a pointer from a list that gets loaded from the external flash into RAM. And that then determines whether we jump into a function that is either in ROM, so originally unpatched, or loaded into RAM if patched. And so each of your references in like Binary Ninja, Ghidra, whatever, is like 3 levels deep. And so you don't get nice cross-references and so on and so forth. And because I didn't have a nice map on what memory is read-only, read-write, and so on and so forth initially, I had to write a lot of scripts to essentially optimize this away. And there are like hundreds of these functions. Okay, so reversed a lot of that stuff, wasted a ton of my time, but hey, at least we understand what's going on. Now, interestingly, you already guessed it, this chip is getting updates. And so there's a tool on macOS called USB-C Firmware Flasher. And this tool allows us to flash firmware onto the chip. And we can actually flash random binaries on it, but the updates are protected with RSA3072. Which, you know, is even today fairly difficult to crack, to say the least. Fortunately / unfortunately, depending on whether you're Apple or whether you're me, the signatures are only checked during updates, and so there's no actual secure boot. And so if you get code execution once, you get persistence for free, because once your stuff is on the external flash, your patches are there, there's no more verification. And so once that's done, we are in business, essentially. And now you saw we could do this with our JTAG probe, and we could just do it in hardware and so on. But like, I have a MacBook that has like a small bulge because I have the JTAG connector soldered in on the bottom, and that's just not very ergonomical to work with. And after looking at the somewhat leaked schematics of the device for a while, I knew that the ACE2 has SWD to the system on a chip, but I also saw that there's another line going back that essentially is a GPIO going to the programming port of the ACE2. And so essentially the SoC seems to be able to debug the ACE2. And so on the SoC, there are somewhere 2 GPIOs. And those GPIOs, if we mess with them, like if we could essentially bit bang debugging port. And so this is called Apple GPIO or something. And there's essentially a memory range in kernel memory that if you write to it, you can control these pins. And luckily, Asahi Linux reversed all of these things because they need to control the GPIOs to turn the backlight on or whatever. And so we knew how to talk to them. And then there's Sigusa's IO kernel read-write extension, which allows us to write from user space into kernel space, which is a terrible idea if you'd install this on your main machine. But for me, it's really, really useful. And so we can control the pins that talk to the debug port of the ACE from software. And so let's bit bang SWD through the kernel. So I built a small tool that essentially is a user space application that talks to IO kernel RW in the kernel, which then writes to a memory map peripheral, which then controls the physical pins, which then talks to the ACE2. And so I wrote a small tool called ACE2 dump, which essentially does all this. And so this allows you to get the firmware of your ACE2 by simply disabling zip, installing the IO kernel RW stuff, and then you can get the firmware. Because previously, I said it would require opening up the MacBook, filling in there, and so on and so forth. Now, I don't just want to dump, I also want to debug, right? And so I decided to also port this whole thing to OpenOCD and essentially build what I call Tamarind kernel, which is an OpenOCD driver that lets you bit bang SWD on Apple SoCs to all GPIOs. And if you look at some of the schematics, you will see that there's more than just the ACE2 that can be debugged on some MacBooks. And so this is actually, Apple has an internal kernel module that does, I think, pretty much the same, but this is an open source implementation where you don't have to worry about any tooling, any leaks, and so on and so forth. And you can find it on my GitHub. Now, did all of that, played around a bit, wrote a Flash driver to be able to update the Flash from user space and so on and so forth. And remember how it loads patches from Flash? Well, guess what function can be patched out? So, and this is awesome because it essentially allows us to do persistent backdooring of the ACE2. And then you can, it survives the full system restore. You restore the system, the ACE2 is still backdoored. It doesn't do anything useful. And I honestly didn't spend too much time on the ACE2 because the ACE3 was there. And so my main question was, can we do the same on the ACE3? Now, the ACE3 is also from Texas Instruments, as we can tell from the small logo on top. And at the time where I did this, there was zero public information on it, literally zero. And it's used on the iPhone 15 and also on the MacBook Pro with M3 Pro and Max processors. And this is interesting, because if you want to fiddle around in the hardware on an iPhone 15, it's super annoying. Everything is super tiny, everything is super compact. You can't actually execute code on in user space that talks to the kernel and so on. But on the MacBook Pro, you often have debug ports, you have nice test points, everything is big enough that I can desolder it, and so on and so forth. And so I ordered a MacBook Pro M3 Max in the hope that I could reuse my software-based attack. Now, the ACE3 doesn't use the USB-C firmware flasher. In fact, it uses its completely new lib ACE3 updater. And they even use different upgrade mechanisms seemingly between the iPhone 15 and the MacBook Pro. And so on the iPhone 15, I think they might even be doing something with SWD. Also, the updates are personalized. So it's not just one signature, but it's actually personalized per machine. And there's like the whole Apple signing server bullshit in between and so on and so forth. So I decided to try the GPIO SWD attack we just talked about to somehow get access to the ACE3. Now, the big problem is, we don't have the schematics of this device, and so we don't know which GPIO of the device actually controls the right pins, right? And so what do? We essentially have the ACE3 and the processor with all its, hundreds of IOs, and 2 of these random IOs will go to the chip, hopefully, maybe. That was my hypothesis. And so the solution is brute force. We just toggle these IOs randomly until we hopefully find the right one. Don't ever do this, like for real. The good news is Amazon has a 30-day return window, so I wasn't as worried. Because your random stuff happens, like the keyboard turns off, this turns on. Unfortunately, it didn't work. And so the question is, send it back, or, And so I decided to grab my screwdriver and let's take a look inside. And when you open up the new MacBook, you can actually directly see these debugging ports that we already saw on the previous MacBooks. And nicely enough, from probing around, they seem to have the same signals as on previous MacBooks. And so I was pretty confident that I knew the debug pinout of this chip. And so here we have the ACE3. Here we again have the external SPI flash and then the debug connectors. So I started probing around with a needle probe and tried to access the debug port with a physical programmer and so on. And I used needle probes because I didn't want to solder into it because, again, 30-day return window. So unfortunately, it didn't work. But I could at least confirm that the GPIOs that I guessed were the right ones. Like I could, with the logic analyzer, check that I actually found the right GPIOs with my software control. So debug port is disabled. So let's dump the flash. And this is, again, if you don't want to solder, terribly annoying because you have to put the probes very precisely here. And somehow some flash programmers don't really work on it well. And so a few dozen attempts later, I, luckily enough, got access to the firmware, or well, to the flash contents. Unfortunately, these flash contents, reversing time, were again just patches and not the entire firmware. And all the peripherals, like all the memory addresses, everything was different. Like there was almost zero overlap between the old one and the new one. And what's very worrying, there were regions with very high entropy, which generally indicates like encryption keys, hashes, whatever, and so on and so forth. So I kept staring at the hexdump for a couple of hours, and eventually I was able to identify a couple of CRCs and so on. And I figured out, hey, let's just flip a bit, fix the CRCs, and see if it still boots, right? Like that's the easiest way to see, does it still boot? 19 days left on the return window. Unfortunately, this doesn't work. I can't get it to boot a modified firmware, but at least I didn't fully brick it, right? Like after flashing it back, it's booted, and the problem here actually is, once you flash it, it stops charging. And so like you have like a couple of hours, and you will see why this gets really annoying later on. Okay, yeah. And then, so yeah, I couldn't find any issues. I actually found like a timing side channel to enumerate the commands that it supports, but I couldn't find any way to get like code running on there and so on. And so either I'm bad at reversing, which is the likely answer, or they are good at engineering, or both. All right. Yeah, but what's interesting is I mentioned previously there are multiple ACE3 chips for each USB-C port. And so what happens if we take the flash dump of another ACE chip, right? And so I compared them, and it turns out that the different ACE chips actually run different firmware. And the back left port is essentially the biggest firmware, it does some more fancy stuff that has been documented before. And there are only some minor differences. Unfortunately, the high entropy regions are part of those differences, so it seems like they have different signatures. So to confirm this, I tried to flash the ACE firmware of the top right to the top left, and it doesn't boot. And so transplanting firmware doesn't work, so probably some per-chip personalization for a freaking USB-C controller. I mean, that's pretty... Yeah, so in the end, what I tried, GPIO SWD access, physical SWD access, modifying the flash contents, fuzzing, and so on and so forth. And so at this point, we have a completely undocumented chip. We have no firmware. We have only some simple commands. And so time to give up. No, because I believe in fault injection. So essentially, the idea is we introduce faults into the chip, which can lead to undefined behavior. So we can modify the behavior of the software running on the device, and hopefully, flip a bit, maybe an important bit, and so on and so forth. And there are different techniques for these. You can do like voltage fault injection, laser fault injection, BBI, and so on and so forth. It has the minor issue that it very often bricks chips. And remember that the freaking MacBook costs $3K, and so each brick chip is like $700 for a USB-C controller. And so, yeah. Now, I first considered doing voltage fault injection, where essentially we drop the supply voltage for a very short amount of time at a very precise point in time. Unfortunately, this pretty much requires soldering, which, again, is not what I want to do. And also the removal of capacitors. We also don't know the actual power supply of the chip, and so I would have to take it off because it's BGA and figure out, hey, where's the main voltage, and so on and so forth. And I didn't want to do that. However, there's another technique called EMFI, electromagnetic fault injection. And with EMFI, we essentially create a very high voltage pulse into a coil, and that lets us inject current in a very precise location on the chip. And so with this, we can potentially skip instructions, and so on and so forth. And no target prep is necessary. Essentially, we just take our EMFI device, we point it at the chip, we zap it, and the chip is hacked. Amazing. Simple enough. Now, unfortunately, we need to have very precise timing on when to inject our chip, which, if you don't know anything about the chip, is fairly difficult to achieve. Side channels. My idea was that I could use maybe a side channel to figure out when in time, my modified flash stops booting. And so my idea was that I take an SDR, which is not the tool for the job, and a very cheap EMFI coil, which is again also not the tool of the job, to measure the electromagnetic radiation of the chip as it boots. And so essentially we point this thing onto the chip and we capture the magic chip waves, and this will hopefully tell us when to hack the chip. And this actually works. Like if we look at the radio spectrum, we can see activity there. Now we don't know what this activity is, but it's something. And so I thought we do, some simple DSP. We essentially start recording the spectrum. We reboot the ACE3 via ACE tool, and then we take a look at the results. It's going to be so simple, right? And so after spending like a couple of hours or days writing random DSP code to somehow get a signal that looks like something meaningful, I eventually was left with this. And I decided, just by feel like this looks like it might mean something. The problem is, for side channels, you want to do a ton of recordings. You want to collect hundreds of samples to essentially get rid of all the noise of the other components, right? Like if the CPU is doing something, it might mess with my signals. The problem is, as I do the recording, my recordings are not aligned. They start at different points in time, and so I need to get them to be at the same time base. Otherwise, I just average out my signal. Luckily, the HackerF actually has a trigger input, and so we just need to find a trigger signal that works well. The nice thing is, we have access to the flash pins, and every time the chip reboots, it will essentially pull the chip select line low. And we can use this signal as a trigger for our HackerF to start the recording. And so essentially we start recording on chip select, which sounds simple, but unfortunately it's broken in the latest firmware of the HackerF, and so I had to downgrade until I found one where it works. So again, a couple of hours wasted. Then reboot the ACE3 and get a perfectly aligned recording. And so, if you do a photo op, it looks like this. If I do it at home, it looks like this mess. So yeah, very, very easy. We have the probe, and we have the chip select line, and then we get perfectly aligned recordings. Amazing. And in fact, if you look at them like visualized, they are pretty stable. There's a bit of noise in there as always, but it works. And then I realized that I recognize these signals at the beginning, because these match up perfectly with the flash activity I saw. And so yeah, nice, we have a side channel and we did all that work, but how does this actually help us with timing our glitch, right? Well, my idea was, I changed the flash contents to be invalid, then I reboot and record and so on and so forth, and then I compare the differences. Sounds simple enough, but you have to remember I have to re-put the probes to flash it, try flashing until it works, realign all the probes, make sure they're exactly aligned again, measure, repeat, and so on and so forth. And then I found that with the original firmware, the spectrum looks like this, and with my modified firmware, that doesn't boot because it fails all the checks, it looks like this. And so we can see that the difference is here at the beginning, and so maybe we glitched there. But I wanted to verify the assumption, and my idea was that, hey, I have these CRCs. In theory, if I fix these CRCs one by one, it should fail later, 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 later. So original firmware, nice. 1 of 3 CRCs correct, we get again the early fail. 2 of 3 CRCs correct, unfortunately no difference, looks exactly the same. But then when 3 of 3 CRCs are correct, we can see that it changes much later. And so this kind of confirms, first off, that our signal actually means something that is useful to us, right? And it also confirms that, hey, maybe we just try to glitch here. All right. Next problem. The location on where you inject the glitch is super important. Unfortunately, literally, and so normally you use like a nice CNC-controlled, thing to position it nicely and so on. Unfortunately, like literally a week earlier, I destroyed my CNC by getting 230 volt on the ground. Don't ask. It's. And so my thinking was, I just take the biggest probe I have that's as big as the chip, and skip all the alignment crap. I told this to some friends who do this professionally, and they laughed at me. So yeah, we have the chip shouter, then I use the chip whisperer for triggering, I have my trigger connection and a ground connection, and so on and so forth. Not shown are the days of debugging. And again, this is the photo op. Reality looked like this, and if you move, like it will all fall apart essentially. And so my first attempt was, I will try to change the version string, because in the firmware I can see the version string. Let's change it, because I can very easily read it out from my computer, from user space. And so here you can see we are running firmware version 45. I changed it in the flash contents, and then I started to essentially glitch it. And so we armed the Husky and the chip shouter. Actually, this was all running on the laptop under attack, so the laptop was glitching itself, because I needed access to the status and so on. And so we arm the Husky, we reboot the ACE3 via ACE tool, which will trigger the reboot that triggers the CS. And then remember how we can see the status on whether it's in application bootloader or bootloader mode. Well, we can actually use this to confirm whether our glitch was successful, because we can see that if we install the wrong firmware, it will go into something called ADFU mode. And so we do this, and we write this is literally the Python script. It's like 20 lines or so. And then we let it run, and you can see we get like one glitch per like 1.5 seconds or so. And that's where the trouble starts, because essentially, sometimes the ACE stops responding, and then we have to auto-reboot. But if we reboot, while one ACE has an invalid firmware, the MacBook stops charging. And so then we have 8 hours until the battery is empty. Then we have to reflash the ACE3, recharge the MacBook, and start over. And now this is like the point in time where you're like, okay, either I build a battery emulator, which might take more time than I need to get to success, or I just try this a couple of times. So I did the lazy way and just tried it a couple of times, and eventually I got a success. I changed the version number on the ACE3. Yay, we glitched the ACE3. Nice. However, remember that we can only modify patches, but we don't know what the patches patch. And we have no input or output, so even if our code is running, how do we get data out? How do we get the firmware out? And so I was thinking maybe I put a loop in there, I can measure it via EM, and so on and so forth. So we can replace functions, but we don't know the functions. However, remember these 4cc commands, right? I built a script that searches through the code, through the patches for all these 4cc commands, and eventually I found this function, which has a lot of 4cc commands, and I thought maybe they patched the same function on the ACE2 as they did on the ACE3, because on the ACE2 I can figure out how is this called, when is it called, what can I do there. And so ACE2 to the rescue, and eventually I found an almost perfect match where the same function was patched on the ACE2 and the ACE3. And this is the USB-W command handler. I have no idea what the USB-W command handler does, but I knew I could call it from user space, because I can send this USB-W command, and I can patch it. And so the problem is, if you want to build a payload for this, remember that each attempt of a payload takes me like 16 hours until I get a single successful run. So we better get this right the first time. Obviously I didn't, but theoretically. Now, my first goal was, I want to read out the firmware of the chip. So essentially, we want to have a read payload. Luckily for us, remember how earlier we found these memr, memw, and mem handlers? This is an existing read function from the ACE2. And so we can take it, because it returns data to user space. So it does all that I want, essentially. So all I had to do was essentially take the assembly of that function, copy it into my patch flash, and then I had a trivial memory reader working. And so essentially, Apple wrote my exploit payload for me. Amazing. Thank you, Apple. And so this returns 4 bytes at the address. And so, yeah, attempt 2. Replaced the USBW command, went through the whole stuff of glitching, this and that, blah, blah, blah. And eventually, after a couple of hours, it worked. And I could actually I could call the USBW command with an address, and I got something back. If you do a lot of ARM reversing, maybe somebody spots what this is. Any ideas? No? If you turn it around, it's 20.06.00.00, and 2.00.00 is essentially normally the RAM region on Cortex-M. This is the stack pointer reset value. So just by seeing this number, we knew this is actually working. Like, we are actually reading real memory and not just some, random stuff. And so, yeah, we can read and write arbitrary memory. Yay, time to dump. The problem is I could only dump 4 bytes at a time. And I could only do 0.7 or something reads per second. And the battery only holds up for 8 hours. So I had to do this multiple times to dump the freaking firmware. But in the end, I got a full dump of the ACE3 ROM and RAM. Nice, amazing. And yeah, essentially, dumping unknown silicon is possible. And it's not it's difficult, but it's not super difficult, right? It's mainly persistence. Are you stupid enough to do this for 2 weeks? We can get code execution without having the firmware, which was for me really something I was interested in. And now we can start researching the ACE3. Now the problem is this is all pretty expensive, right? The overall equipment I use is probably $5,000 or so, plus the MacBook. And so I decided to port all of this self-contained onto the chip shouter Pico EMP, which is $60. It's not as good. It takes much, much longer to be successful, but it's only $60. And so if you ever want to destroy your MacBook or something, you can now do it for $60. So yeah, but now we are ready to actually do research on this new ACE3. I started emulating it, and it's actually, I think it's a lot of fun. So thank you all for coming, and hope you enjoyed this.
Thank you, Thomas, for this great presentation. We still have a couple of minutes left, so if you want to ask a question, you can line up at the microphones, or we can also take questions from the internet. I see someone running to the microphone, so the first question is yours.
Did you return the MacBook?
It's classified. No, actually, I sold it to a friend, but I told him what I did, and I gave him a good discount.
That's at least a nice thing to do. Do we have further questions? Someone else is running. It seems to be the running job here.
What about ACE1, and what kind of software were you using? I saw Binary Ninja. Could you please describe your software stack?
Yeah, Python and Binary Ninja. That's it. And ACE1, I have no idea.
All right, one more question. The microphone at the back, please.
What kind of signal are you injecting exactly?
With the EMFI probe?
Yeah.
Just the pulse.
Okay.
All right, one more question over there, please.
Yeah, so how someone could get into something like this, or does someone do it for a hobby or a job, or?
Yeah, for me it's a healthy mix of hobby and job. If you want to try fault injection, I actually have a couple of setups with me. So if tomorrow you can come, send me a message on Twitter or so, and you can play around with a bit of fault injection. Awesome.
Thank you very much for all the questions. If you have further questions, Thomas will be answering them afterwards outside of the room. Thank you very much for this really entertaining lecture.
you.